So, I know that starting out a video by saying you may not enjoy this, and also this thing that I did may not be very special, isn't exactly, like the best way to start a video, but I just want to manage expectations and not waste anyone's time, so let's keep this here as brief as possible. If you don't like math, as many of you told me in the comments of the last video where I did math, telling me that I would ruin your algorithm, fair and obvious warning, you're not going to like this video. For those of you still around, look at this behemoth. Here it is, because if you're like me and this video didn't just pop up in your recommended, you've searched up the term ternary to decimal equation, or some base to some other base equation. But unlike me, you have this video to watch. See, before this video, and you can go check this out for yourself, for whatever reason there was not a single website, video, forum, or message board that had this equation written out. Granted, I don't know how extensively I really searched. I searched ternary to decimal equation, looked through the first page of Google, binary to decimal equation, looked through the first page, base x to base y equation, and then eventually I gave up and asked several AIs. I asked the Snapchat AI and ChatGPT, both of which tried to give me the process for converting one base to another, or gave me lines of code in Python or other programming languages to convert one base to another. But once I said no, I want an actual mathematical equation, not a function or a process, both AIs told me none existed, because it was an iterative process, which I, of course, took as a challenge. So here we are with this groundbreaking discovery I've made that will change the face of mathematics forever, right? No, not even close. I imagine that this is something someone has already come up with, but just isn't well known because of its incredibly limited use. First of all, there's the problem of its sheer size and overwhelming girth that makes it hard to handle and would frankly be a mouthful, a problem with which I'm all too familiar. So you may be inclined in most, if not all circumstances, to implement one of these shorter methods that are well documented, or just use an online converter. But that being said, that's obviously not what I did. One, because I thought it was a bit weird that there wasn't an equation for this, so I wanted to see if I could try and figure out why. And two, often when I'm doing hobbyist math, I'm using Desmos's graphing calculator, which, as far as I'm aware, I can't just tell to do a multi-step process. Not to mention, without going into too long of a tangent of what I was doing such that I needed this equation in the first place, I needed a way of examining the specific values of numbers, like all ones in binaries or all twos in ternary, which is obviously going to be easier in those bases. It's for these reasons that even though I am now aware of how relatively uninspired my discovery was, sadly, I'm still surprised that I can't find this anywhere else on the internet, but I guess that's enough rambling about my shock. So why was this, well, as I said, discovery so uninspired? Simple. Size isn't the only reason why this equation goes unused. Well, I mean, technically it is. Let me just show you. This equation is actually doing two things, and not just one. It converts any number of any base into base 10, and then converts that base 10 number to a number of any base. So now, when you look at it like this, you may notice, if you haven't already, what these two equations actually are. They are just the methods of conversion that are already well known. To convert any number of any base, you simply take each digit, multiply them by the base to the power of the position of the digit. So all we have to ask ourselves is how we would represent that using only the functions available in Desmos, for example. We know that we are going to have a summation of some sort since we are adding these parts together in a clear and distinct pattern. It is the sum of each digit times the base to the power of the digit. Since the sum can iterate from 0, since we start at 0 for the first digit, that means that here we have the sum of the digit value per iteration times the initial base to the power of k, from k equals 0 to the number of digits minus 1. Now all we need is the number of digits, and the specific digit per iteration given a specific input in a specific base. The latter of which may seem difficult, but it won't involve that base at all if you, or the calculator you are using, evaluates this all in base 10. If I type 1010 into Desmos, it won't think I'm saying 10. It will think I'm saying 1010. So an easy way to get the value of a given digit is to do mod in 10. Which, in case you don't know, just gives you the remainder when dividing n by 10. Mod 1410 is 4. 1310 is 3. Here it gives us the first digit. However, continuing this, you'll notice that there's an issue. Mod 114 is 14 and not 10, let alone the 1 that we need it to be in order for this to work. I think the solution to one of these problems is easy. Once we can isolate the number, in this instance get it to be 10 instead of 14, all we need to do is divide by the appropriate power of 10. But how do we isolate the number? This is going to sound crazy, but this is one of those problems that gets easier when it gets harder. If we move on and do mod 1114 1000, that's 114, which means as it goes on, it concatenates or adds on all previous numbers. So all we have to do is take the modulus of one iteration minus the modulus of the iteration before it to get the current digit. However, we need to remember when we actually go to write this, as confusing as it may be, when we use this modulus method, we are talking about a power of 10 greater than the current digit. So once we put it all together, it will look like this, and this is essentially done. Because we could put infinity for this upper bound as far as I care. It would just concatenate infinitely many zeros in front of our number, but we're not going to notice. But of course, to briefly go over the more satisfying answer, 10 to the 0 power is 1, which has 1 digit. 10 to the 1 is 10, which has 2 digits. 10 to the 2 is 100 with 3 digits, and this just goes on and on and on. For all whole numbers, 10 to the power of that number has 1 more than that number of digits. If our number were to be expressed as a power of 10, which is to say that 10 to the x equals our number, then x equals log n. In this case, however, x would not be a whole number. Well, not unless our number is actually a power of 10. But in order to fix that, we simply take the floor function of log n to get a whole number for x. Now we have that x is 1 less than the number of digits in our number. Or in other words, the number of digits in our number is floor log n plus 1. You could go through a similar process with the other part of the equation, or the other equation, however you want to say it, and you could use the method that people generally use to convert a base 10 number into a number of another base, but I think what I'm about to show you is much easier to understand. First, here we should know that we're going to have to examine each digit like we did in the last equation. This time, however, instead of putting something together that is broken, we are going to have to take something apart, if that makes any sense. If it doesn't, we'll just keep going and hopefully you'll see what I mean. First, let's say that we have part of our equation that gives us the proper output for each digit per iteration. We need to take that times 10 to the power of the iteration and then add it all together in order to get our number. For the digit in the 0 position, or the first digit, it's very easy. In binary, it will be alternating zeros and ones. For ternary, it's 0, 1, 2, 0, 1, 2. And the pattern just carries on like that for higher bases. So for the first digit, it's just mod, number, base. Moving on to the next digit, since we're just counting up, once the first digit resets, we finally count up in the second digit. For binary, you will see that this means that it alternates 0, 0, 1, 1, 0, 0, 1, 1, and ternary 0, 0, 0, 1, 1, 1, 2, 2, 2. If you look at this pattern across all bases, clearly as we move up in bases, we will see that the lengths of these straights will increase by the power of the digit depending on the base. For binary per digit from position 0 to 3, the straights are 1, 2, 4, 8. For ternary, it's 1, 3, 9, 27. The pattern there being base to the digit. And so for the next part, I'm gonna keep it real with y'all. I could probably come up with a more sophisticated way of explaining this, especially if we stuck with describing the base 10 to base n process. This is the quotient per iteration, and this gives us the remainder per iteration. And if you can't go watch a video on this process and understand what I mean by quotient and remainder, let me just keep it simple then. Dividing, make graph flatter. So this probably go here, but that no good because need to go by whole number. So boom, and like that, there's the full equation. Same deal with the upper bound as before. It could be infinity if you want, because it's just gonna keep dividing nothing and then adding it on infinitely. But I think the proper thing to put up there is log n divided by log base, or was it like floor log n divided by log base? I don't know. I'll let you nerds figure it out. Likewise, there may be ways of simplifying these equations, or other things that you can think of. Obviously, you're more than welcome to do it. I just wanted to share this as is so it was out there, because like I said, it's just kind of weird that it isn't. Nobody's done this before, which makes me worry if it works or not, but as far as I can tell, it does. Just obviously not in a base higher than the one you evaluated in. And in the case of how this equation was written, that's base 10. But yeah, if you guys want to see more videos like this one, let me know. But if you don't, I suppose I don't have to ask the internet to tell me what they don't like about my content, because oh boy, do they do that all the time unprovoked already.